A very good morning and welcome to this course on the foundations of continuum mechanics. Today we'll be talking a bit more about the indicial notation. So the topic for today's lecture are going to be tensor-tensor products. So till now we have talked about vector products, vector dyad products and dyad-dyad products. So we will generalize that to products of nth order tensors. We'll also talk a bit more about notation in indicial notation, and then we will talk about the relationship between the orders of tensors and the number of free indices that appear in a given mathematical term. We will talk about an interesting topic that is called contraction in indicial notation, and finally we'll talk about the idea of symmetry in terms of nth order tensors. So let's get started. So in the last lecture we talked about the products of vectors with dyads and dyads with dyads. But if it works for a dyad, which is actually a second order tensor, the products and the rules should also work for second order tensors or in general for the nth order tensors. So today we will talk about products of vectors with tensors and tensors with tensors. So rather than talking about vector tensor products, which is just a special case of tensor-tensor products, let's talk about tensor-tensor products. So let's discuss this through examples, and this time we'll straight away jump to tensor double products. So let's say we have two tensors A and B, and we'll try to find out what A horizontal double dot B is. So let's start with the analogy with dyads. So when we had dyads, we had a dyad UV which was multiplied to a dyad WP, right? And we would write the dyad, well, let's say these are the two dyads. So the indices we had were UI, VJ, and we would have WK, PQ. We still haven't applied the double dot product yet. And then when we applied the double dot, we would have a UV horizontal double dot with a WP. So this would be UI, VJ, and then if you remember, the double horizontal double dot results in WJ PI, which is from the definition of the horizontal double dot. So you will need to remember this, that the vectors V and W, the adjacent ones, get dotted. So the indices I typically remember through the order of indices. So in horizontal double dot you have IJ and then you have a JI. So if I was to do it for second order tensors A and B rather than these dyads, so I would write, instead of UV dyad, I'll write a second order tensor A and a second order tensor B, and then indicially this would be AIJ BKQ, because second order tensors will have two indices to represent them. And then when we apply the horizontal double dot, we will have indices in the order Aij, and then we'll have a BJI, just the way we have the ordering of indices in this dyad. So therefore we can say that the horizontal double dot of A and B is given as Aij BJI. So it's very analogous to what we had in dyads. Similarly, if I want to write the expression for the vertical double dot, so that becomes A vertical double dot B is Aij Bij. We can also talk about tensor single dot. So if I say the tensor A single dot with the tensor B, then this would be very analogous to what we had in dyads. So let's use the analogy. So when we had UV dotted with a WP, we notice that the adjacent vectors got dotted. So initially this was ui vj and then wj pk. We'll follow the same in second order tensors. So we have a tensor single dot with a b tensor. So this becomes aij and then bjk. Okay, so this allows us to write the expression for a single dot between tensors a and b. So I can write a tensor single dot with a b tensor is nothing but aij bjk. Now you see that I'm mixing symbolic and indicial notation, but I'll allow myself this because expressing this otherwise using symbolic purely is quite difficult. And in this course, typically we'll want to work with indicial. So I'll allow myself this just to explain the definition of the single and double dot products dealing with tensors. So now let's move to the next topic in today's lecture, that is a bit more on notations. In fact, we'll call it the misuse notation. It's very important to discuss this because many people get confused when they read this kind of a notation in books and texts, but this is quite common, so we must discuss this. So I'll tell you what I mean with by this misuse notation. So let's start with what we know. So we write a vector v as VIEI, which basically expands to the three components V1 E1 plus V2 E2 plus V3 E3. So VIs are the components and EIs are the unit vectors or the bases. It's plural, so it's with an E. You may have seen, and we discussed it in the beginning, that in the indicial notation, we represent it as Vi with square brackets. But what the misuse notation means is that sometimes we'll write this simply as Vi. And why is it called the misuse notation? Because Vi till now we said refers to just the components of V. So V, if I put I equal to 1, I get the first component. If I put I equal to 2, I get the second component. And if I put I equal to 3, I get the third component. So to differentiate the components from the whole vector, we used to put this square brackets. But in the misuse notation, we remove the square brackets and we accept the fact that Vi actually denotes the whole vector V. Now, when do we take VIs as components and when do we take Vi as the whole vector? Well, that is context dependent. So depending on the context in which it appears, you would consider that. So again, this comes with experience. So in the beginning, you can take it by rule that Vi is a component, but depending on the context, you may have to accept or understand Vi as a whole vector V. So I'll write it down that it is context dependent. Similarly, by the same logic, we'll have sigma ij, which will denote a whole tensor. So it has two free indices here, I and j. So it's a second order tensor. So it may denote a whole tensor rather than denoting just a component of that tensor depending on the values of I and j. So again, it is context dependent. So it may denote a whole second order tensor. So I've written a may, or it may denote just a component. So now let's move on to the next topic for today's discussion, that is called the number of free indices and the order of tensor. So we will have this discussion through examples. So the first example is the tensor sigma single dotted with a vector v. So in the indicial notation, I would write this as sigma ij vj. I'm sure now you can understand the indicial notation because it's a single dot. So the right index of sigma and the index of v will be the same. If there's any confusion, please feel free to write the tensor analogous to a dyad of two vectors and do a dot between the adjacent vectorial terms. So the indicial notation for this is sigma ij vj. And the question is, what is this quantity? Well, we know this is a tensor, of course, but what exactly is the order of this tensor? Now, if you were to expand this, again, I'm using the misuse notation here that I am assuming this to be the whole tensorial quantity rather than just the one of the components of the tensor. So what exactly is the order of the tensor sigma ij vj? Well, there's a rule that we can follow. So we count the number of free indices in this quantity. So let's look at that. So the only free index here is I. So we can say I is free and the index j is dummy. So the number of free indices is 1, which is actually equal to the order of the tensor. So if you recall that in the beginning of the course, I asked you to be very careful when using the idea that the number of indices in a tensor is equal to its order. That was because it's not just the number of indices, it is the number of free indices. And we have seen this in the past lecture again and again, that it is the number of indices which are free that is equal to the order of the tensor. So let's establish that through a few more examples. So in this case, we have the outer product or the dyad of u and v, which in the misuse notation will be written as ui vj. Although I should be writing it as this tensor, but I will get rid of these brackets and use the misuse notation here. So how many free indices do we have here? Well, we have a ui and a vj, so we have two free indices. Which amounts to a total of 9 components, because the index I can go from 1 to 3, the index j can go from 1 to 3. So this is indeed a second order tensor. So we have established again that the number of free indices is equal to the order of the tensor. So this is the second order tensor. Let's take another example. So this time I'll write the indicial notation to start with, because with tensors of higher order, it's much easier to represent them with indicial notation. So it's sigma ij epsilon ik. Now whatever this denotes, I simply have to find the order of this term. So what you do is you count the number of free indices. So then the free indices here are indices j and k. So I'll say the order of this tensor is equal to 2, because there are two free indices which are j and k. Another example here, sigma ij epsilon ij, which actually is the vertical double dot between the second order tensors sigma and epsilon. So what is the order of this tensor? Well, let's count the number of free indices. So what we notice here is that there is no free index here, because both indices I and j are repeated. So since the number of free indices are 0, so this is a 0th order tensor. or a scalar. So let's take one last example and then we'll move on. So we'll take the outer product of a vector and a second order tensor this time. So in the initial notation, that will be written as ui sigma jk. And that's how we do an outer product, that we don't repeat the indices because it's an outer product. It will increase the order. So in an outer product, we will not have any common index because of the definition of an outer product. So what that means is that we have 3 free indices here. So the order of this is 3. So this is the third. So this terms ui sigma jk, it actually denotes a third order tensor. And you can check that. I mean, you have 3 free indices. Each index can go from 1 to 3. So you'll have a total of 3 to the power of 3. That is 27 components here. And our pattern check that we established last time also works. So u has order 1, sigma has order 2. So in the outer product, we'll have 1 plus 2, that is equal to 3 in the order of the output or the result. All right, so now that we have established the fact that the order of a tensor is equal to the number of free indices, let's talk about a very important concept in indicial notation, and that is called contraction. So contraction basically means that we set any two indices equal in a term. Well, I'll show you through many examples, but before that I would like to let you know that contraction is performed to move from an outer product to an inner product. So I'll write that down and then we'll see that through examples. So whenever you perform a contraction on an outer product, you actually get an inner product. So there is a relationship between outer and inner, and that is established through the contraction operation. So let's look at contraction through examples. So the first example we will take is a vector tensor product. So let's take ui sigma jk, which is what we just saw in an example previously. So this is the outer product of the vector u and the tensor sigma. So what is the order of this? The order of this is 3 because you have 3 free indices in this term. And now I'll perform a contraction here. So what does contraction mean? Contraction is an operation where we set two indices equal in a term. So I perform a contraction where I say that the index I is equal to the index j. So that's a contraction. And this is the outer product. So what is the resultant inner product? Let's have a look. So when you put I equal to j, what you get is ui sigma I k. And let's find out the order of this expression. So we have just one free index, that is k here. So the order of this is 1. Okay. So what we saw was that we were able to define an inner product between a vector and a tensor using a contraction here, which is I equals j. And what we also noticed was, as we have done in the past, that a contraction reduces the order by 2. So we started with a third order outer product, and when we performed a contraction, it reduced the order by 2. So 3 minus 2 is equal to 1. So 3 was the order of the outer product and 1 was the outer of the inner product after applying a contraction. So let's take more examples and understand the idea better. So the other example is simply the outer product of u and v. So what is the order of this outer product? Well, we have two free indices I and j, so the order is 2. So the only contraction we can perform is I equals to j here, because there are only two indices, so they are we'll make them equal. And when we do that, we get ui vi, which we know is the dot product of vectors u and v, which is actually a scalar, and you can see that here as well because we have no free index now in ui vi, so the order of this is 0, right? So again we see that we were able to define an inner product, that is ui vi, using an outer product ui vj by applying a contraction on it. In fact, let's take the first example, which is this one, ui sigma jk, and try to apply another contraction here. So we apply a contraction which is I equals k, because we have three free indices in the outer product ui sigma jk. So we can also apply I equal to k, because the contraction only says you make the two indices equal. So I set I equal to k. So what I get is ui sigma ji, which is a different thing than what we had earlier, but its order is still 1 because we have applied a contraction. In fact, we could also create an inner product by setting j equals to k. And there's no problem here. It's allowed. I mean, it's not necessary that the two indices have to come from different quantities. Sigma's indices j and k can also be set to equal to each other. So what we get is ui sigma jj, which again is first order because we have only one free index I in this expression. Okay. So let's take a few more examples and reinforce the idea of contraction taking us from an outer product to an inner product. So the order of this term epsilon ijk sigma pq, and you can consider epsilon to be a tensor here, although we'll discuss epsilon being a tensor later when we talk about the tensor transformation property, but for now you can assume that epsilon is a third order tensor. So what are the number of free indices here? We have I, j, k, p and q, which is 5. So this expression has a total of 5 free indices. Now what I want to demonstrate to you is that we can apply two contractions at the same time to generate an inner product out of an outer product. So let's do that. So we apply a contraction I equals to k, that's one, and the other we apply is j equals to q. So let's see what the final expression is. So we have an epsilon I j, well, let's not do this because then it will make two terms of the epsilon the same. So let's apply I equals to p and j equals to q. So this becomes epsilon I j k sigma I j, and in this case we only have one free index now because I and j are repeated, so only k is the free index, so the order of this is 1. So what we noticed was that each contraction results in reduction of the order by 2. So let's write this general rule. Each contraction reduces the order of the expression by 2. So the outer product had 5 free indices, so the order was 5, and the inner product only has 1 free index, so the order is 1 because we applied 2 contractions. I'll also want to talk about product between two second order tensors because that's important for us, so let's do that. So the outer product is Aij Bkq, where A and B are second order tensors. So the order of this is 4 because we have 4 free indices. Now I'll apply one contraction, which is j equals k, and this results in the expression Aij Bjq, which has an order of 2. So one contraction resulted in the reduction of the order by 2. And what exactly are these in the symbolic notation? Well, left hand side is simply the outer product of A and B, so which is written as AB, whereas what you see on the right hand side is the single dot between A and B, right? And if I apply two contractions this time, along with setting j equals to k, I also set I equals to q. So that results in Aij Bji, which has an order of 0 because there is no free index here, and in fact symbolically this is the horizontal double dot between the tensors A and B. So I hope you are able to understand the idea of contractions which take us from an outer product to an inner product. So inner products can easily be defined using contractions on outer products. So let's move on to the last topic of today's lecture, that is on symmetry of tensors. Well, you have some understanding or intuition of symmetry from the idea of matrices. So let's discuss this through examples again. So we say sigma ij, which is a second order tensor in the misuse notation, we say it's symmetric if sigma ij is the same as sigma ji. Now that's a bit confusing because we are using both the misuse notation and the component wise representation here, but you will get it with time. So that's again context dependent. So sigma ij is the complete second order tensor here. So on the right hand side we are saying that sigma ij equals sigma ji for all values of I and j. So let's look at from a matrix point of view. So if I see the matrix representation, I can see that, well, I already know that if these terms are equal with the same color, then the matrix is symmetric. So generally speaking, that can be written as indicial notation wise, sigma ij equals sigma ji for all values of I and j. Of course, it results in sigma 1 1 equal to sigma 1 1, sigma 2 2 equals sigma 2 2, and sigma 3 3 equals sigma 3 3. Well, that's trivial, so that doesn't give us anything interesting. But if you put I equal to 1 and j equal to 2, you get sigma 1 2 equals sigma 2 1, and so on. So that is something we already understood from a matrix point of view. But let's talk about symmetry in higher order tensors. So if I have a third order tensor sigma ijk, how do we talk about symmetry in this case? It's very difficult to draw it because you'll need a three-dimensional paper, but we can use the same rule as we have used here. And that is, if we talk about symmetry in a tensor, we have to talk about the indices we are talking about in terms of symmetry. So we say Cijk is symmetric in the indices I and j if Cijk is equal to Cjik. So if I simply say C is symmetric, that will not have any meaning by itself. That will be very vague. It's not complete. So I have to specify the indices in which the matrix or the tensor is symmetric. So it could even be the case that C is symmetric in the indices I and k. So in that case, we'll write Cijk equals Ckji. So both 1 and 2 are completely different. They may or may not be true at the same time. So this is something one has to specify clearly. Now if we talk about symmetry, we can also talk about skew symmetry. So we say sigma ij is skew symmetric if sigma ij equals minus sigma ji. Now here we don't have to specify the indices I and j because there is no other way. So there is no lack of clarity here. But if you go to higher order tensors, then you will have to specify that. So what it means here is that in the matrix representation, the terms sigma 2 1 and the terms sigma 1 2 are related as sigma 1 2 is equal to minus sigma 2 1 and so on. Let's talk about higher order tensors. So we say Cijk is skew symmetric in, so now we have to specify the indices I and j if Cijk is equal to minus of Cjik. So epsilon, as we said, we can assume this to be a third order tensor. So think about it. Well, you should pause the video and think about it. That is epsilon skew symmetric? Well, we can check. So let's talk about skew symmetry in I and j. So epsilon ijk, compare that with epsilon jik. So here, if I write this way, so ijk is one order, whatever that is. If I swap the indices j and I, then the order changes. So now I have jik, which is the reverse order. So if you swap any two indices, then the order of indices in epsilon changes. So its sign also changes by the definition of the permutation symbol epsilon. So what that means is that epsilon ijk is skew symmetric in any two indices. So we can just write epsilon ijk is skew symmetric, and that will be a clear statement because any two indices you take, epsilon will be skew symmetric in those. So this brings us to the end of this lecture. So in this lecture today, we talked about tensor products, some indicial notation to help us understand the products of tensors. We talked about the very important idea that is called contraction, which helps us to take from outer products to inner products, and we can apply multiple contractions at the same time, which results in each contraction resulting in a reduction of the order by 2. Then we talked about symmetry and skew symmetry, and we established the fact that the order of a tensor in the indicial notation representation can easily be found out by counting the number of free indices in the indicial notation. So we'll have a tutorial in the next class where we'll solve problems from the topics that have been discussed in this week. Let's do a quick concept check. So we have 4 mathematical terms provided to us, and for each term we have to find out the order of the tensors that are given to us. So remember, the order of a tensor is simply the number of free indices in that tensor. So please have a look and count the number of free indices, which will actually be equal to the order of the tensor. So thank you, and I'll see you in the next lecture.